Welcome to the Explainer, everyone. Today, we are stepping into the ring. We're looking specifically at Cambridge Syllabus Code 0580, and we are treating mathematical investigations like a tactical boxing match. Have you ever looked at a chaotic real-world exam question, the kind that makes your mind go completely blank, and wondered if there's a hidden strategy to just crack it open? Well, today we're going to learn exactly how to turn messy, complex observations into powerful, elegant algebraic rules that score maximum points. We're going to use a strategy I like to call float like a concept, sting like evidence. It's all about hitting the examiner with a perfect combination of answers, the jab, the cross, and the knockout hook. So let's decode the universe together, start building your ultimate exam strategy, and get right into it. Let's start with a classic challenge that might seem completely impossible to solve just by looking at the page. Imagine you're sitting in the exam hall. The clock is ticking, and you're faced with a real Cambridge mathematics scenario. If 3 airplanes cross paths, how many times do their smoke trails intersect? Now, you might be able to sketch that out quickly in the margins of your paper, but what if the question asks about 100 airplanes? Drawing 100 intersecting lines by hand would literally eat up your entire exam time, and honestly, you'd probably lose count halfway through. I see 2 typical types of students here. Let's call them Alex and Sam. Alex panics, overloads the answer box with raw mathematical facts, but provides absolutely no analysis. Sam, on the other hand, rushes the question, completely misses the command word requirements, and tries to guess the answer. Both of them lose crucial marks. This is exactly why we need a structured framework for mathematical investigations. To solve these massive problems without the massive manual work, here is our agenda for today's session. First, we'll tackle the plane trails puzzle. Second, we'll break down the hidden treasure algorithm. And third, we'll look at graphing inequalities with tech. Let's jump straight into Section 1, the plane trails puzzle. Our first investigation begins at an aircraft show where planes are flying in various formations, leaving these brightly colored smoke trails behind them. In exam terms, this is where we throw our first punch, the jab. We need to make sharp, quick observations based on the physical clues. We have to establish our point, the P in the famous PEL framework. By observing the visual evidence, we immediately notice that the plane's formation totally dictates how many times the trails intersect. Think about it. If the planes fly in a strict parallel formation, their smoke trails are never going to cross, giving us 0 crossing points. If they slightly adjust their paths, we can easily spot a formation that yields exactly 2 crossing points. And if we have 3 planes flying completely independent, non-parallel routes, their trails can produce a maximum of 3 crossing points. Right now, we aren't solving the whole exam paper. We are just gathering our raw, indisputable evidence. We are floating like a concept, getting a feel for the problem's boundaries. Now, good mathematicians and top-scoring students don't just collect evidence randomly. They organize it. This is your cross combination. We need to map out our findings and put the results of our investigation into an ordered table. This is the evidence stage of our PO framework. We clearly define our variables for the examiner. Let the number of planes be P, and the maximum crossing points be N. For parallel planes, the value is 0. For that specific 2-crossing formation, it's 2. For 3 planes, we hit a maximum of 3. This table right here is the absolute critical bridge between raw, messy observation and undeniable mathematical truth. If you don't draw a table in an investigation question, you are practically throwing grade boundaries away. Examiners actively look for this structured data. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, moving on. Here is the million-dollar question, the moment where you earn those top marks. Take a second to mentally predict what formula could perfectly map out the crossing points for literally any number of planes. We know the results for a small number of planes because we just tabulated the evidence, but we want the master key that unlocks the entire system. We need to decode the core command words. The question usually asks you to find an expression or state the algebraic rule linking P and N. This is where your analysis has to kick in. This brings us to the knockout blow, the hook, generalization. This brilliantly illustrates the ultimate goal of the entire 0580 mathematical investigation syllabus. Generalization is the crucial process of moving from those specific, tabulated pieces of evidence to a universal algebraic rule. In our PEL framework, this represents the explanation and the link. It's the strategy that lets us solve the puzzle and guarantee the maximum intersections for 100 or 1,000 planes, without ever having to sit there and sketch them out. You find the pattern in your table, you formally write the rule linking your variables, and the mystery is solved. The red pen marks from your teacher turn into big green check marks. Let's move on to Section 2, the hidden treasure algorithm. For this act of our strategy session, our investigation shifts from the open sky to a tricky treasure island puzzle, the kind of complex algorithmic question that Cambridge loves to throw at you. Here are the rules of the game, and you need to decode these command constraints carefully. There is a buried treasure hidden in one of 12 treasure chests, which are all arranged in a circle. 12 contestants stand by the chests. The elimination rule is strictly alternating. So, the treasure is not in chest 1, so we cross it out. Chest 2 is left alone for now. Chest 3 is crossed out, chest 4 is left alone, and chest 5 is crossed out. This pattern of eliminating alternate chests continues, looping around the circle iteratively, meaning repeatedly, until only one single chest remains. That final chest holds the treasure. Students like Sam tend to rush reading these constraints. If you misread alternate chests iteratively, your entire mathematical model collapses. Let's break down this cyclic algorithm step by step so you can see exactly how to lay out your working for the examiner. In round 1, going around our circle of 12, we systematically discount all the odd numbers, so chests 1, 3, 5, 7, 9, and 11 are officially out of the game. We are left only with the even numbers. Now, crucially, we continue our alternating pattern seamlessly into round 2. Starting from where we left off, we must now discount chests 2, 6, and 10. Going into round 3, we knock out chests 4 and 12. And just like that, through logical deduction, the only chest left standing is chest 8. The treasure is hidden right there in chest 8. Notice how methodical this job is. We are perfectly following the constraints. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions. Right, back to the puzzle. What happens when the rules change? What if the television show producers unexpectedly alter the number of contestants playing? Unfortunately for you, in the exam hall, the parameters will change. What if there are 4 contestants, or 5, 8, 9, or even 15? If you don't have a strategy, you'd have to frantically draw circles and recount the chests from scratch every single time. Or would you? This is where we run our interactive workshop challenge. I want you to mentally scan this data. We are pulling out our most reliable exam hall weapon, the table, the cross-punch. We tabulate our findings for the different numbers of contestants, formally defining n as the number of contestants and x as the winning chess. By manually playing out the game for a small sample size, say 4, 5, 8, 9, and 15 contestants, and plugging those winning chess numbers into this table, we are setting ourselves up to reveal a completely hidden numerical sequence. This is the exact moment where your mark potential goes from 50% to 80%. You are organizing chaos into structure. Think about your time management matrix during an exam. We have to contrast these two approaches heavily. On one side of the screen, you have the completely tedious process of counting out alternating chests manually for every single scenario. It's incredibly slow, it eats up your time, and it's highly prone to human error when you're under stress. On the other hand, you have the elite strategy, the efficiency of discovering the overarching mathematical rule. By finding the algebraic link between the winning chest x and the number of contestants n, we bypass the manual labor entirely. This is what separates an average student from an exceptional one. Using the specific patterns we discover in our table, we gain a massive strategic advantage. We can instantly predict the winning chess for massive, complex games. If the exam paper suddenly throws 31, 32, or 33 contestants at us for 3 extra marks, we absolutely do not panic. And we certainly don't start drawing 33 tiny chests on our scratch paper like Alex would. No, we simply plug the new n value into our generalized algebraic rule and calculate the winning chess in mere seconds. That is the incredible time-saving power of mathematical generalization. You've hit the hook and secured the points. Finally, let's step into Section 3, graphing inequalities with tech. For our final case file, we're looking at how modern information and communication technology handles these exact logical boundaries. Once we truly understand a generalized mathematical rule, we can leverage tech to visualize it instantly. Look at this visual evidence. This screenshot perfectly demonstrates how a graphics calculator interprets a basic linear inequality, a mathematical rule that establishes a very specific boundary. Instead of just plotting a simple static straight line, the calculator understands the underlying algebraic rule and automatically shades the correct region. In the specific case, the vast area to the right and below the diagonal line. The processor is basically testing millions of coordinate points instantly to see if they fit the mathematical parameters we gave it. And here we see another crystal clear application of this. This time, the technology is efficiently graphing a horizontal bounded region. The strict mathematical boundary is plotted straight across the y-axis, and the entire logical region above it is shaded perfectly. The device does all the heavy graphical lifting of visual representation, which allows us, the mathematicians, to focus purely on the logic, the command words, and the overarching strategy of the problem. Notice how beautifully this tech comparison parallels our earlier discoveries about manual drawing versus algebraic rules. Manual inequality graphing requires testing coordinates by hand, carefully drawing your boundaries with a ruler, and shading with your pencil. It's necessary to know, but it's slow. Graphics calculator graphing, however, completely automates the plotting and shading steps that would normally consume precious exam minutes. Ultimately, whether it's through tech or through your own algebraic formulas, our goal is the same: implementing a system. Remember the 3 rules that guarantee top marks. Decode the command word, apply the PEL framework through your tables and formulas, and utilize the time management matrix to know when to calculate and when to generalize. Students who implement these exact mathematical strategies see an average improvement of 2 full grade boundaries. But honestly, that only happens if you practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @aceexams_IGCs and click that bell. Don't let another exam pass you by. Today, we've navigated the chaotic trails of airplanes, solved a deserted island treasure hunt, and mastered the digital screen of a graphics calculator. You are now equipped with the ultimate 0580 toolkit, observing physical clues, organizing them by tabulating your evidence, and generalizing those patterns into powerful mathematical rules. So drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every single comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. I'll see you in the next explainer.